Okay, thank you all for being here today for this periodic seminar. Today we have the chance to have Ishfaq delivering the seminar. He is a new PhD student at the lab. If I have to say a few words on Ishfaq, now I have to read. He's coming from Pakistan, where he's holding his master's degree from University of Tashila. Right, in Pakistan.
Yeah.
And he has been working for the past 4 years and a half in the field of embedded systems, and mostly specialized in energy and performance optimization in reconfigurable MPSOM architectures. Today he will be talking about a multi-core processor platform for energy and throughput aware applications. So you will have around 30 minutes to entertain us on the subject, and I don't know if you want to be interrupted when you are delivering the talk, or you want to go to the end.
I'll talk about it like in the presentation. Yeah. I would like to have question answer session at the end, but if someone has something important to ask at any point in time, you can surely interrupt me.
Okay. Perfect. So 30 minutes.
Thank you. Thank you very much, everyone, for being here today, and thank you, Betty, for the introduction and the kind words. This is basically the project in which I basically worked as a design engineer, and this project was basically funded by National ICTR and the research donor agency just like FCT over here. And this project was basically the brainchild of Dr. Yasir Qadri. This was his initiative to start this project. The sequence of presentation is something like in the very beginning I will give a brief overview of the research project in which I worked and the research team, which was basically divided into two parts, like hardware team and the software team. I will briefly introduce those teams, and then afterward I will basically discuss very briefly that why we need to reduce energy consumption in multi-core processors. What is the problem? What is the issue with those multi-core processors? What is our proposed solution, and how we come up with the AI and bio-inspired algorithm-based solution which basically reduce energy consumption without a major impact on the throughput of the systems. And the simulation setup which we use in order to validate the results which were obtained using AI and bio-inspired based algorithms and results, and then afterward I conclude my presentation with the conclusion and research contribution, and finally there will be a question answer session at end. So this project, again, a multi-core processor platform for energy and throughput web application. The main idea behind this project was basically to find such an AI-based algorithm which basically reconfigure dynamically system resources as per the requirement of application, so that we can save maximum power without a major impact on the throughput. And there were around 22 members in this project, and the overall team was basically divided into two different parts: hardware development team and algorithm team, or software development team. And I was basically part of this algorithm and software development team, and my objective basically being part of the algorithm team includes AI again and bio-inspired algorithm based design space exploration technique which was implemented on software. And at later stage, the same methodology was being implemented on real-time hardware like FPGA, and it was being verified that whether the results which software team got was either correct or not. And now the question is, why we need reduction in energy consumption? Well, energy efficient system design has become a necessity because of very rapid increase in the use of portable devices like laptops, PDAs, and smartphone, and the portability requirement of these devices put a very severe constraint on energy consumption. Also, energy efficient system design is important in high-end desktops and data servers because of costly packaging and complex cooling systems. And last but not the least, global industrial initiative of green computing put very severe constraint on energy consumption. So basically we need an AI and artificial intelligence based energy reduction techniques for multi-core processors. There are various techniques which are being proposed in the literature. We broadly we can divide them into three different categories. logical level, microarchitecture level, and the system level. Logical level energy reduction techniques can further be divided into clock gating and power gating techniques. Clock gating technique is very effective basically technique which can basically reduce dynamic power by reducing the number of gate toggling, and it can be done by either reducing the number of gates or by reducing the number of times each gate toggles. And the second one is power gating. In power gating is relatively more effective because it can reduce both static power and the dynamic power. And this basically technique is mostly used in various sleep modes of different processors. At microarchitecture level, we can reduce energy consumption by exploring the major energy consumption components such as cache memory, pipelines, and buses. And finally, logical level and microarchitecture level provides energy reduction techniques at lower abstraction level. At system level or high level, basically these provides another level of energy saving technique, and we work on basically system level techniques and more specifically on the reconfiguration techniques. And this is the main idea behind reconfiguration technique is somehow to switch off those modules which either has low impact on the throughput or it has no impact at all on the throughput. So this is how we reduce energy consumption. So contemporary processor, in this specific slides, I'll try to differentiate between contemporary processor and reconfigurable architecture. Contemporary processor unfortunately do not leverage much flexibility for reconfiguration, and also they are designed for overall and average performance. But on the other hand, reconfigurable processor provides a better option to reconfigure the system resources so that we dynamically reconfigure system resources and reduce energy consumption. But we again need to go beyond simple frequency scaling and core switching. And as we know that more like larger the design space is, more the complexer it becomes to explore it. So basically we need, rather than just exhaustive and random search exploration, we need some intelligent algorithm which basically explore the design space in lesser time so that we can reduce maximum energy consumption. So we basically, in order to overcome this problem, we basically suggested AI-based algorithm, AI-based exploration engine, which takes energy consumption, throughput, and mix ratio as the input parameter, and based upon these input parameters, it suggests us 4 output parameters, which include number of cores, operating frequency, L1, L2 cache size, and L1, L2 cache associativity. And these output parameter was being suggested by taking input energy consumption and throughput for a specific application. And the architecture which we used was basically Intel x86 architecture, which includes 16 cores, around 256 KB of cache, and up to 80 megahertz frequency. Here is a list of algorithms which we use for the exploration purpose. This is just the list which I have explored. My team basically explored many other algorithms as well, but for the timing, I'm just discussing those algorithms which I have explored, which include fuzzy logic type 1, fuzzy logic type 2, and company optimization, genetic algorithm, and estimation and distribution algorithm. Here is a brief comparison of our state-of-the-art algorithm with some other suggested technique, and there are two mainly important things to compare. One is that the architecture parameter, which this is, by the way, is my proposed solution, and these 5 are the other state-of-the-art techniques. And as you see that in our case we have relatively larger design space, and also we have a bio-inspired algorithm for design space exploration, which suggests different optimal solution. But relatively in these techniques there is no AI or bio-inspired algorithm which basically suggests system resources. They are using exhaustive search algorithm for reconfiguration purpose. So from now onward, I'm going to just discuss about one of those algorithms because I guess it would be very complex and difficult to talk about all of those algorithms. So I'll just discuss ant colony optimization. What is this ant colony optimization? Basically, this algorithm is inspired from the natural behavior of ants to find food source. So how this works basically, in the beginning, different ants start randomly by for the search of food, and they take random paths, and if an ant find a food source, it spread fragrant material on their way to back home, which is normally called pheromone, and the quality of this pheromone material is that it evaporates with the passage of time, and the more the complexity, more the intensity of this fragrant material on a specific path is, more ants are being attracted toward that path, and that path is selected maximum time. So this simulation also shows the intensity of that pheromone material, like from yellow is the minimum pheromone material, green one is that it's relatively more, and the red one shows the more complexity of that pheromone material. So as you see that with the passage of time, the smaller path gets more intensity of that pheromone material, and so the chances of being selected, the chances of selection of this smaller path is relatively increasing with the passage of time. So Marco Rodriguez was the first one who basically generated a mathematical model based upon this behavior. This is basically a probabilistic selection, like in order to select any specific node, we need to generate, he generated a probabilistic equation which basically involves pheromone material, like the intensity of pheromone and some heuristic to select a specific node. So I guess in order to discuss before this probabilistic model, I need to discuss the model which we need to in order to use ant colony optimization. First we need to convert our problem into a simple model that is called traveling salesman problem, which basically involves that we need to convert our problem into different set of nodes. Like in our case, since we have number of cores, cache size and frequencies, so what we did, we basically generated different clusters for each parameter of multicore processors. For core cluster set, we have a complete cluster. Similarly, for cache, we have another cluster, and for frequency, we have the last cluster set. And also, the number of ants which we use for the exploration purpose was also put in another cluster. So each ant basically select from each cluster, select a node in each iteration, and the selection of any node during any point in time is being done using this probabilistic model. And by the way, in each of these nodes is basically, for example, for core, it includes energy consumption and throughput value. And similarly, for cache, we have cache, energy, and throughput values, and so on. Okay? So, then once a node is being selected, depending upon its effectiveness and optimality level, different updates are being done, like local pheromone update and global pheromone update. And finally, these values are being incorporated in an overall update. So that, and these updates are being done so that the chances of selection of any node which has come out as the best node in the previous iteration are relatively more in the next iteration as well. So here is the overall exploration engine, which is kind of feedback system, which takes energy consumption and throughput values, scale them between 0 and 1, and then again a solution component arrangement is something like we need to convert our problem into different cluster sets, and based upon this arrangement we generate a probabilistic vector, and based upon this probabilistic vector, a node is being selected and different values of data are being done, and finally these values are fed to multicore processor for the simulation purpose, and and then after simulation those values are fed back in order to compare it with the inputs. The experiment platform which we use for the validation of results include like for the implementation of code we use MATLAB and M3 Explorer, and for the simulation purpose we use microarchitecture system simulator, SCSC simulator, Ubuntu, Splash2, CACTI for cache assessment cycle time, and various mathematical model in order to calculate energy consumption and throughput. Here are the results which we obtained using these techniques. Default configuration basically involves the maximum number of cores, caches, and frequency. And since energy consumption and throughput is scaled between 0 and 1, so it includes maximum energy consumption and maximum throughput. And after 7 iterations, our algorithm suggested the best solution. So it was found out that energy consumption was also reduced to a drastic level without a major impact on the throughput. And these are the results which were obtained during different iterations before the final iteration. From this point onward, I'll be discussing this final solution and the default configuration. Like default, I'll basically compare the maximum resources with the one which was obtained at the end of algorithm. Yeah, please.
So, what kind of application was it like? Because this is some application, right?
Yeah.
You said that you will have 16 cores and this,
Yeah.
right? And then based on that application, you applied your algorithm.
Mhm.
So, what kind of application?
There were 5 different benchmark applications, more specifically bonds, FM, Chelsea, Water Splash, and Lose. These were basically chosen from Splash2 benchmark application, and these are the standard benchmark application for the evaluation of performance. So these are the 5 ones which we use for the evaluation purposes.
So, you use all of them?
Yeah, for more specifically 5.
And what kind of characteristics do they have? Are they memory intensive or like?
They basically involve, for example, if I talk about FM, it's a Fourier transform implementation in 3D. So there are basically different applications which were written in different codes, and they are not only like memory extensive, they are complete, like they explore all the parameters like cores, memory, and frequency.
So it was like you extracted their parameters first, or
Yeah.
you had the numbers already, as you said that you have, like for your system parameters, you have this number of cores and the misses and all these things. So you use some kind of simulator to extract these parameters, or you were working on the code and you did it yourself?
No, first of all, we worked on the simulation part. We run almost more than 100 execution, 100 simulations, and we generated this model first, which includes energy consumption and throughput values for different benchmark application. And then we run our algorithm on this specific model, and we found out that these configurations are relatively better for this specific application. And then we again tested it on the simulator and cross-checked whether the solution which was being given by algorithm are correct or not, and that it was found out that it is quite valid. Okay. So again, the energy consumption values were calculated for these 5 benchmark applications, and after comparison, like for bonds, blue one is bonds, FMM is in red, green one is Chelsea, and water special, and like indigo and yellow is blue. So it was found that for all the 5 benchmark application, our proposed solution reduced energy consumption between 70 to 76%, and average 77% reduction in energy consumption was observed. Then in order to see that with this much reduction in energy consumption, what was the impact on the throughput of the system? So it was quite surprising for us as well that it was between 10 to 20% reduction. So an average only 7% reduction was on throughput was observed. So with like 77% reduction on energy consumption, only 7% impact on throughput was, so that was a lot more energy and cost reduction. So EDP is basically the parameter which basically gives a more insight of what was the trade-off between energy consumption and throughput, and it is being obtained by simply multiplying energy and delay. And again, the comparison for all of these 5 benchmark applications, there was around 74% reduction in energy delay product. So lower the energy delay product is, the better the system is. So as you see that around 74% reduction in energy delay product means our algorithm was quite effective in this for these 5 benchmark applications. And in this specific slide, I am just showing what was the impact on energy delay product against different benchmark application individually. So our algorithm by reducing, our algorithm basically verified that the optimality of optimality and like verified like end-term optimization can reduce energy consumption without a major impact on the throughput. Therefore, we can use this specific algorithm for real-time hardware implementation. These are 2 research contributions which I have published in 2 different journals. Yeah, thank you very much.
So we still have room for a few questions.
No, the question is about the heuristics. So do I understand correctly that it's like 4-dimensional search space since you have the 4 petals clusters? Is it correct?
It's not 4-dimensional. I would say it's 2-dimensional. Like for example, if we first time selects from this whole cluster set, selects 1 node during first iteration, and that for 1 node again another node is being selected from the cache sizes cluster, and then similarly from 3rd cluster again 1 node is being selected. So in each iteration, each node from each cluster set is selected.
Imagine I'm not using heuristics and I'm writing the optimization problem, linear program or something. So this means I will have 4 arrays of variables.
It depends that how complex your design space is. Like in our case, since we have selected 4 parameters, so we have a 4 cluster set. But in case if you have more parameters in your design space or subspace, then it would be like more clusters. You have to add more clusters in your problem.
And wait, at the beginning you were talking that there were many heuristics, then you focused on end colony. Is it because it was the best results, or it was mostly because you were mostly working on the end colony? What was the choice for end colony?
There were unfortunately at this point in time I haven't discussed all the reasons, because there is few work which is still in review phase. So unfortunately I haven't discussed that issue. But yeah, there were mainly 2 reasons. One was that end-colony optimization come up with the best solution in less number of iteration. So like in 7 iteration it gives us an optimal solution, and you probably know that if we increase the number of iteration for the exploration purpose, we we need to have more energy consumption for the exploration, which adds up more overheads in terms of energy consumption. So lesser the iterations are, the lesser the energy consumption for the exploration purposes. So that was the one condition, and also that was one reason for selecting end-colony optimization. The second reason was that relatively end-colony optimization results, both in terms of energy consumption and throughput, were relatively better as compared to other algorithms.
Another questions?
Okay, so on your slide you were having this default thing. So by default, what do you mean that it's a default setting? So you don't apply your optimization algorithm and you just run it? Like how?
Default is basically the maximum.
I'm concerned about these. Like you simulated them, right? It's not on the real hardware thing. You simulated these results. So when you were doing the default configuration, you just, because you had all these parameters of energy and this thing, and then you run them without optimization, and then you measure the energy consumption, and you say that okay, these are default results, right? And then you run the thing again, and then you apply the optimization scheme, and then you measure the energy efficiency, right? That's what you were doing, or something else?
Yeah, exactly. I mean, the idea of the default configuration which you mentioned earlier, that we were like comparing that if we, without using the algorithm, if we run the same application on maximum resources, or what was the energy consumption and throughput parameter, and by using our optimization algorithm, what effect it do to the energy consumption parameter, and by comparing both of these configurations, we came up with the idea that our algorithm was reducing the energy consumption for different benchmark applications without a major impact on throughput.
Okay. So I have like another question is related to the actual hardware implementation. You said that you guys implemented something on the actual hardware.
Yeah.
So
Again.
Like sorry. So I just want to ask that. So like because now modern processors have all these things like MP-SOCs are so advanced that they are already doing this kind of stuff. Like although this like it is nice. Like, but I assume that, for example, the research in the Intel or the new processors that are coming, that are really like they are somehow using these things. So actually, what I wanted to see that like, although I think it's, I don't know if you did it or not, that comparison with the real hardware stuff. Like if somehow you can compare your approach with the i7 or whatever. So you did something like this, or it was?
Basically, it was being done by our hardware team on the real-time systems, and the thing which you mentioned that it is being done by some other companies. At that point in time, there was only two things which was being executed on the real-time hardware, and that was only dynamic frequency scaling and the code switching. Cache sizes and its associativity was not included in the whole design space. Like. And both L1 and L2, and as you know that since we increased the design space, so our design space was relatively more complex, and you probably know that increasing more parameter in the design space, the complexity of exploration increases exponentially. Like you can't do it by using simply exhaustive or rule-based exploration. You can't do it at that point in time. So you basically need some algorithms for that specific purpose. And at that point in time, only frequency scaling and code switching was being done by Intel, and I have just mentioned it. And our hardware team, they implemented one of the algorithm on real-time hardware like FPGA. They basically use FPGA board, and they ported Leon 3 processor, software processor on that FPGA processor, and then they use a fuzzy logic based reconfiguration technique on that Leon 3 processor, and they find out that the reduction in energy consumption was not that much as it was being observed on the software, but yeah, there was a reduction in energy consumption, which like a reduction on throughput.
What was the difference like in terms of energy consumption?
What was that?
What was the gain or the loss?
Unfortunately, I don't remember it yet, but yeah, they have also, they have published that work in different journals, but for the time I can't remember exact number, like it was between like 10 to 20 or 30 or 40%, I don't remember it yet, but yeah, there was a reduction in energy consumption in throughput.
One last question. Okay.
Which simulator did you use to extract these parameters from the benchmarks? Do you have any name? I can use it for myself.
I don't understand your question.
So you got all. So if you go to your slides, you were saying you have these inputs, where you say the misses and all these things. So you run an application. You know how many times it will access the cache, how many times it will. What is the time on the processor, and how many times it will access the bus. You got these readings, right?
Basically, these
I got it.
Yeah, These were in terms of these were instruction cycle simulators. So they give the performance of systems in terms of instructions. So those were being collected. There is very extensive Excel sheet which was being generated.
So I'm just asking about the simulator, like you use some simulator, right? This
FMM, yeah, exactly.
This benchmark you run on some simulator, it gave them some, that this
Instructions,
benchmark will access instruction cache this number of time, or it will miss, like it has the cache misses thousands.
Yeah.
So I'm just asking about that simulator.
Yeah, like we do have like the evaluation of system was being done in terms of instruction cycle, like hit rate, miss rate, that was being calculated using either number of hits, number of misses, number of cycles, and by multiplying, I mean, energy consumption and throughput values, we calculated the overall energy consumption and throughput, and that was being calculated by using an extensive mathematical model. Unfortunately, I haven't discussed those models as well because, again, I was having no contribution in those mathematical models. That was being was suggested by Dr. Ishfaq, and those are very complex equations.
You made those, no, I asked you earlier that I think it is just benchmarks you had, like, so you had benchmarks and you used a simulator because you mentioned many simulators, you said you used them. So I was assuming that because these are fixed benchmarks, right, which you use, they are already there. So you run them on the simulator, and simulator gives you some results.
Yeah, here there is something like the simulator gives us number of cycles, hit rate, miss rate, okay? And we incorporated those values in a mathematical model, and mathematical model gives us energy consumption and throughput values.
Yeah, I am asking about not the energy consumption, the previous values. So I was just asking about this name of the simulator.
And I have mentioned, like, I mean, those are the 5 benchmark Mars, it was being executed on the Mars. Yeah, you are talking about Mars?
Man, I don't know. I was just asking you the name because I was interested.
Okay, it was basically Mars simulator which was executed on using two Linux platforms.
Okay, thanks.
Then just to close this question session, I will put the last one. Right?
Yeah.
So the thing is that when you simulate to extract all those numbers, you have to simulate for a number of times, right? Define a number of times. How do you determine that simulation time? And how, I mean, what will be the impact of the simulation time on the accuracy of your results?
Yeah, that is a good question. I mean, initially we put no constraint on the number of instructions and we just keep on executing it. So it was found out that it takes very large time to come up with the optimal solution. So we, with the passage of time, we start reducing the number of iterations because again, more number of iteration means more overhead. So finally we came up like from 100 we switched it to 50 and then 25. And finally we came up that 7 is a point by which we can have less overhead and also we are getting better solution. So finally we put a constraint like 7. 7 was a.
That was that empirically true. I mean, it was empiric number that you choose, or it was proven to be.
That was random exploration, like we started it from 100, then reduced it to 50, then 25, and then we keep on reducing it, and then finally we came to know like 7 is the optimal point where we can set it, and by this way we can have a better results without major impact or overhead.
So we were waiting for you to close the session. Thank you very much, everybody.